Hey everyone, let's continue on a few more examples from trig problem solving here. So from our assignment sheet, this is example number 3, and you're going to see kind of that same pattern of problem solving that we did in the first example, or I guess what we did in the previous chapters with problem solving. We want to draw a good diagram, and we want to make sure things that are fixed lengths or fixed angles are shown by that, and things that change in the problem are represented by variables. So the angle the sun is a variable, and the length of the shadow is a variable, but the tree is going to stay 10 meters tall, which gives us two variables, and we actually have two rates, which is good. We have a change in an angle, decreasing radians per hour, and we have a lengthening shadow. So two variables, two rates, perfect. So the next thing you want to do then is you want to figure out what ratio is best suited for this. And again, because it's tangent, opposite over adjacent, or cotangent, adjacent over opposite, we want to know which one is going to be easier to work with. If you thought you'd work with a tangent ratio, you're going to have to either use the product rule, x tan theta equals 10, or tan theta equals 10 to x minus 1. So that's what you would work with if you did tangent. If you work with cotangent, and you kind of just clean it up, you get 10 cotangent equals x. And this is my choice. I'm going to work with cotangent in this one. So again, it doesn't matter. You could have chose tangent to work with, but I chose cotangent. Derivative of cotangent is negative cosecant theta. And again, if this was more complicated than theta, you would have to use the chain rule. And in this case, because theta doesn't match t, you get d theta dt. Derivative of x is 1, but again, because x's and t's don't match, you get dx dt. So now you got your angle rate and you got your shadow rate. Perfect. What you don't have, though, is you don't have the cosecant ratio. So as we solve a problem again, we draw a diagram. We've got variables. We've got fixed lengths. We pick our best ratio. We put rates in. Now we want to solve for the moment of time. And like we talked about in the past, we got to be able to figure out some information on our own. So we go to the moment in time, and we're told the angle is pi over 3, or for people who don't like radians, you need to change that to 60 degrees. And what is the cosecant ratio for 60 degrees? A lot of us will say, well, I know the sine ratio for 60 degrees is root 3 over 2, which means then the cosecant ratio is 2 over root 3. So unlike the last example where you kind of had to figure out using a trig identity, this one is just easier because you're given the angle. So then if you have 2 over root 3 is cosecant theta, all you got to do is square that. So again, if you went back to your formula, it was negative 10 cosecant squared theta, right, to d theta dt equals dx dt. Plug, and away you go. So 40 over 9, which is 4.4 meters per hour. So that's an example of solving, I guess, when you know the angle. All right, let's do another example in this video. Let's do number 4. So again, to kind of look at the same information given to us, draw a diagram. What's variable and what's fixed. The ladder length is not going to change, so we can call that 8. The height of the ladder up in the wall is going to change, and the angle is going to change. So again, we're talking about the ladder sliding down the wall, so that's why the height is there. We're not talking about the horizontal distance moving away this time. So I've got two variables, which gives me two rates, or two rates, which give me two variables. So that matches again. Opposite over hypotenuse, so I'm going to talk about either being a sine ratio or a cosecant ratio this time. Again, if I was to kind of cross multiply and clean things up, which one do I want to work with? And I'm going to work with my sine ratio. It's easier than working with a product rule, and it's easier than working with a -1 exponent. Again, the derivative of sine is cosine. Derivative of theta, because it's respect to time, ends up being a implicit differentiation, right? d theta dt. Derivative of h is 1, but again, the h doesn't match the t, so it's 1 with dh dt. So now I got to basically draw my new diagram. I want to draw the moment in time diagram, and then I need to figure out what the cosine ratio is. So here we go. My moment in time, the angle is pi over 4, or the angle is 45 degrees. So here's my moment in time. The angle on the bottom is given to me, and my ladder is still 8. Cosine of pi over 4, root 2 over 2, or 1 over root 2, depending on how you want to simplify that. In this case, a little bit of fraction work. The 2 times 4 is 8, cancels with the 8. You're left with the negative root 2. So there's another example in regards to solving with trig. Same idea, draw a diagram,
put your variables as variables, put your fixed rates as fixed lengths as fixed, or fixed angles as fixed, and then work on a ratio. Differentiate, put the rates in, solve, draw a new triangle for your moment in time. Such a great little triangle there. It doesn't take long to draw that, and then solve. All right, we're going to do another video here right away for a couple more examples.